everyone, and welcome to the podcast, Life is a Story We Tell Ourselves. I'm your host, Don Murphy. In this episode, we will delve into the quantum world. With competing ideas of how to interpret the meaning of quantum mechanics, physics is in a crisis. Can an ancient concept known as the One rescue physics? From Bohr's Copenhagen interpretation to the MiniWorlds theory put forward by Hugh Everett to the seemingly intractable problem of quantum gravity, the challenges facing physics threaten to tear down the very foundation of the science. In an attempt to save physics from itself, Heinrich Pace has written a compelling book, The One, that offers a solution rooted in the concept that everything we see in the universe, including ourselves, emerges from the One, and surprisingly, the One itself is made up of everything that we see. How is this possible? Professor Heinrich Pace proposes that quantum mechanics can show us the way to the answer once we accept the universe as one. He joins us today to discuss his book and tell us why he believes physics can be saved from itself. Heinrich is a professor at the Technical University Dortmund in northwest Germany. Heinrich, welcome to Life is a Story We Tell Ourselves.
Thank you. Thanks for having me.
Yeah. So let's just get right into it. Tell us, Heinrich, was there a singular event in your life that influenced you to become a theoretical physicist?
Well, maybe not the singular event that made me a theoretical physicist, but one thing I remember was when I was a little kid, or well, not a little kid, but a kid, and I looked through the bookshelf of my parents, and I found this illustrated history of Western philosophy by Bertrand Russell. And I flipped through the pages, and there were all these ancient Greek philosophers introduced, and they thought about the universe and whether it's infinite or not infinite. And these were questions that fascinated me a lot. So I started thinking about these things and talking to friends. And then I heard rumors about Einstein's theory of relativity, and this somehow hooked me, and I wanted to learn more. And so in school, I specialized in physics, and then I realized that was not enough. So I studied physics and was still not enough. So I'm still in the business.
So what do you think it was that made you do this questioning? Was it just spontaneous or just part of your nature? Why did you question in the beginning, or do you think it's just part of our human nature to question things?
No, good question. I think most humans, if not all humans, have some interest in what is reality, what's the foundation of everything, some fascination about the absolute. We are finite beings. We die. We have limited power. So it's interesting to relate that to something bigger, to the universe, to the infinite, to something like that.
So it's like gets into those questions like, why are we here, and what is existence, and some of the questions that came about in ancient philosophy of what is the meaning of life, and of course that evolved into philosophy of nature. And so, yeah, I can really understand that. So let's get into talking about quantum mechanics a little bit. There have been many books written on quantum mechanics, for layperson even. And if you had to summarize quantum mechanics for the layperson, what would you tell them? Where would you begin?
I would say, well, I would start with the observation that in quantum mechanics, waves and particles are not totally different things, but that what we believe is a particle, what is matter, can be understood as a wave, and what we experience as a wave, such as light, for example, has some properties of particles. Mm-hmm. And this is a very fundamental thing in quantum mechanics. And the interesting thing about it is that a particle always has a definite position. We can say this particle is at this position, at this location, or at this position. But a wave is spread out. So a wave has no definite position. It can have, or we can assign many positions to the wave. And so if we understand a particle as a wave, then also the particle can exist in many positions. And then what's fascinating is that we can generalize that, not only to position, but to essentially any property matter can have. So the most extreme example is this Schrödinger cat idea. Erwin Schrödinger, one of the pioneers of quantum mechanics, came up with, who said, a cat, as long as we don't look at it and really determine its state, can be in a superposition of being dead and alive. So that's, I think, the essence of quantum mechanics.
Right, but Schrödinger, to some extent, meant that as I don't want to say a joke, but meant to put a finer point on quantum mechanics and the difficulty in its explanation, because clearly a cat can't be dead and alive at the same time. But he was trying to make a point.
Yeah, that's right. I mean, we don't observe these superpositions for large, big, everyday objects, and it's non-trivial to understand why this happens for small objects, apparently, but not for large, everyday objects. And the process, the agent, which protects us from too much of this quantum weirdness in our daily lives, is a process called decoherence. And I think this is very important to understand quantum mechanics.
And so let's just talk about that briefly for a minute, because decoherence is an important concept. Just explain what you mean by decoherence.
Decoherence is a process that happens when a quantum object interacts with a larger environment. And it's strongly connected to another quantum process, entanglement. So let's start with entanglement first, maybe. Entanglement is a generalization of this idea that particles can be in different states at the same time for objects which are composed of more than one particle. So if I have an object and I know its state perfectly well, it might be that this perfectly well-known state is composed of different, there are different possibilities to compose this object out of constituents. So if we go back to the wave image, for example, if we have two waves, or if we have a perfectly flat surface of a pond or of the ocean, then this can be, if we understand this as a sum of two swells combined, it can be two flat swells, but it also can be two swells which are just shifted by half an oscillation pattern, half an oscillation cycle, so that the oscillation patterns cancel each other. And we don't know what this total outcome, this perfectly flat surface of our ocean, was made from. What were the individual constituents that produced it? So this is essentially the idea of quantum entanglement, that we can know the total state of an object perfectly well, of a composed object, but we don't know nothing about the constituents. So if we go back to the cat example again, if we say we had two cats and one is alive, then this might be that the first cat is alive and the second cat is dead, or the first cat is dead and the second cat is alive. But in the quantum world, it might also be that the first cat is half alive and half dead, and the second cat is half alive and half dead. And the sum adds up to one live cat and one dead cat.
Right, understand. So when most people think about entanglement, these days, or at least in the fascinating part of it, or even getting into the science fiction part of it, they think of two remote particles, like one electron being in Tokyo and one being in New York, and these particles are entangled because you can measure their spin. So if you measure the spin of one in Tokyo, then that's going to determine exactly what the spin is of the one in New York. And this is what Einstein, of course, called that spooky action at a distance, which everybody talks about. And there was a recent Nobel Prize given as a result of this. However, I've read other scientists who are still outliers who don't believe there's entanglement, that believe that there are hidden variables, that believe that there's a problem with locality, that says, we're not interpreting that right. You want to comment on that? Especially since the Nobel Prize was just given.
Yeah. Well, maybe first how I explained entanglement is related to this correlation. If we have this total object, which is made out of, let's say, two spins, as you said, and the total object has zero spin, then one spin points up and the other spin points down, and then you can separate them, and you don't know which spin points up and which spin points down. But in the moment when you measure one spin, you know immediately the other one. This is exactly this correlation you were referring to, and the gist of the experiments which were given the Nobel Prize for. But it's a consequence of this idea that we can know the whole perfectly well, but we don't know anything about the constituents. Then the other question was that people say there might be hidden variables, so that it is not really this magical correlation between things we don't know. These ideas have a good, there's a good reason for these ideas, and maybe to understand this discussion and this argument, it's good to go back to the beginning of quantum mechanics when Bohr and Heisenberg discovered that a particle can be both a wave or can be seen both as a wave or a particle, and these are somehow complementary aspects of the same thing. But at the same time, you can only observe one of these aspects. You can't observe both of these aspects at the same time. And this seems to say that we don't really can see all of nature. We only see a part of it, depending on our perspective onto the object. But Bohr and Heisenberg, they were hesitant to accept this idea of a hidden reality somehow. So they, as many physicists, said, physics is an experimental science, and only what we measure and see we can really talk about and can be sure about. So they argued that what we measure is reality, and that the quantum formalism itself is only a tool to make predictions for this reality, which somehow parameterizes or summarizes our knowledge, but doesn't tell us anything about nature. And in my opinion, and in the opinion of many people, this is very weird, since usually when we do physics, which was my first motivation to do physics in the first place, is I wanted to learn something about nature. I don't want to learn something about human knowledge about nature. So I want a physics theory which is a model for nature. So if we say we want to have a physics theory which is a model for nature, then we can do two things. We can either accept that reality is more than what we see. This is what I would argue for. Or we could try to limit the quantum possibilities to what we see, to constrain the quantum possibilities to the outcome of the experiments. And this is what these hidden variables are trying to do. But what people have found is that it's very difficult to find hidden variable models which are consistent with Einstein's theory of relativity, for example.
Understand. So let's go back to this wave particle notion for just a minute, because it's important to, I think, to understand that in quantum field theory, and correct me if I'm wrong, a particle is really an excitation in a wave. So if you have an electric field, for example, then the excitation in that field, or in the waves in that field, actually manifests. And so when you think of it in that context, it's not really all that surprising that you have this wave particle duality. Is it, or is it still somehow as strange as some people want to make quantum mechanics out to be? Because it's fairly well established that, in quantum field theory, that a particle is an excitation in a wave.
Yes, but it's still the question: what is reality? Is the quantum field just a tool we use to calculate properties of particles, and the particles are real, or is the field, is the wave real, and the particle is only how a wave or a field appears to us when we look at it in a specific way. I'm in the field or wave camp. I think the wave, the field is the fundamental thing, and there are arguments for that. For example, there's a process called the Unruh effect, which says that if we have a detector and we accelerate this detector, then we will see particles, even in vacuum. So these particles come out of nothing. So what this implies is that the notion whether we have a particle or no particle is a consequence of our way of moving, of our perspective on the fundamental reality, and it's not a part of the fundamental reality itself. So I think the wave or the field is more fundamental than the particle itself, but other people have other opinions.
Understand. So from reading your book, The One, it seems clear that you are just as interested in natural philosophy and the philosophy of science and the fundamental questions that ultimately led to physics as a science, as well as, of course, as to other scientific disciplines. So do you think that the divergence of science and philosophy is kind of at the root of some of the problems facing physics in particular?
I definitely think that it would be better if there would be more exchange between philosophy and physics. I think physics really addresses fundamental questions, and there's a big overlap with philosophy, and there should be more exchange, definitely.
Sure. So let's really get into trying to understand this concept of one or monism as it relates to quantum mechanics. So how did you come up with this idea? I know you went to great pains in your book to give a thorough history and connection between the ancient idea of monism and the idea of the one. So could you explain to our listeners exactly what you mean by that and how it's connected in some way to quantum mechanics?
Yeah, it's again related to these two buzzwords we had already, entanglement and decoherence. So entanglement tells us that if we have a quantum object which is composed of two or more individual constituents, that we can know the total, the whole, but we at the same time don't know anything about the constituents. And in quantum mechanics, the properties of an object are all what defines the object. For example, two electrons, which have the same properties, are literally indistinguishable. They are not individual anymore. So if I don't know the properties of these objects in an entangled whole, we cannot really exist that these constituents really exist. We cannot really say that these constituents really exist. So that means that if we apply this idea of entanglement to the entire universe, then it's natural to say, since everything at some point has interacted, that the entire universe is a quantum state, is entangled, and that the experience that we really see individual things that make up the universe, that this is some kind of illusion. And decoherence, the second process we briefly mentioned that we didn't really come to talk about earlier on, explains why, if everything is one, if this single, whole, all-encompassing thing, the universe as a quantum object, is all that exists, why we experience this object as many things. And the reason is decoherence always happens when a quantum object interacts with an environment. It becomes entangled with an environment. But then if we have an observer like ourselves who is local in space and time and doesn't know the entire environment, which is the rest of the universe, she or he will has to average over the state of the environment somehow. And what she or he experiences then is that somehow this averaging splits up the universe into individual parts. And these are these individual parts we see, and not only into individual parts, but also into parallel realities, as comes out from this famous MiniWorlds interpretation by Hugh Everett, that there are parallel realities. Each of them realizes the possibility of the original quantum reality. So, for example, if an electron can be in two places at once and we measure it, then there are two parallel realities. And in one reality, we see the electron in the first place, and in the other one, we see the electron in the second place.
So I'm glad you mentioned Hugh Everett's MiniWorlds concept, because, of course, it's become very popular since the movie came out, Everything, Everywhere, All at Once. And so now, and I guess several years ago, there was a cover story on Scientific American that really brought the MiniWorlds concept into everyone's consciousness. But I think there have been some misunderstandings or misinterpretations of what Hugh Everett meant, because people seem to have gone off into tangents and said, well, what he meant was that there are many worlds out there, and there are doppelgangers of everybody existing out there, and there are many different universes out there. Is that really what Hugh Everett meant? I mean, you seem to be putting a finer point on that and saying that's not exactly what he was saying.
Yeah, I think that's at least not the most important aspect. So, I mean, there are different ways to think about it, and it's always depends on how we define reality, what we call reality. Is reality what we can see and observe, or is reality the most objective thing we can think of? The extrapolation when we abstract of ourselves. And in quantum mechanics, these two things, which usually work quite good together, usually when we make an experiment, we can repeat the experiment, we always get the same result again and again, and we can both see the result, and on the other hand, every observer will agree on the same result. In quantum mechanics, these two ideas about reality, they go in different directions. And so what I think is that the basic idea of Everett is to treat the entire universe as a quantum object, and that this is the most important thing. And then when we ask what is reality, what we see, what we observe, what we experience in our daily lives is, of course, only one single reality. We don't see these parallel realities as an effect of decoherence, due to decoherence. We see only one of these parallel realities. So this is the answer if we say, what do we see and what can we observe? If, on the other hand, we say, if we abstract from ourselves and we ask, what is the most objective definition of reality? It's also not the MiniWorlds, but the most objective reality is then this quantum state where all these different realities are merged together into one single entangled object. So these parallel realities, we can say they exist. We can say it is a little bit a matter of taste whether we say they exist. I would say yes, they exist indeed. There are doppelgangers and there are parallel universes and so on, but they are somehow in between these two definitions of reality. The most objective reality is the one where we have only one single quantum state, which is the entire universe. The most accessible definition of reality is what we see in an experiment. And this, of course, is only one reality.
Mm-hmm. So, do you think we'll ever have access to those parallel universes or those doppelgangers out there? And is there a way, or does the physics limit our ability to ever observe those things? You seem to be saying that the very nature of quantum mechanics prevents us from seeing those all at once, or being able to distinguish them or measure them at a single point in time.
Yeah, the problem is that... Yeah, go on.
Like I was just going to say, like I can't see you and your doppelganger at the same time.
Yeah, that's true. I mean, the point is that decoherence is so unbelievably efficient for large objects that like ourselves or cats or such things. Big, large objects, they all the time interact with the environment. There are photons scattering off these objects, and they are very closely connected to the rest of the universe. And so since they are not separated from the rest of the universe, we don't really see their quantum properties. So we can think of their quantum properties to be delocalized into the rest of the universe. But if you look at only this object, we see a classical object. So it's a consequence of this process of decoherence, which is so efficient that we don't see these quantum effects for large objects.
Understand.
So my guess is we never will experience these parallel realities. But I'm not 100% sure. Science always offers surprises, and who knows, there are ideas that maybe we could time travel and go into parallel realities when we time travel and so on. So ideas going back to David Deutsch and so on. So who knows? But at the moment, I think meeting your doppelganger will be pretty difficult.
I understand. So as we've discussed earlier, I've spent, the last 10 years conducting science seminars to promote science literacy. And when it comes to quantum mechanics, many of my participants in these seminars have succumbed, I guess is the right word, to many New Age interpretations of quantum mechanics, which you mention in your book, and that seems to have happened historically through astrology and various other pseudosciences. And they do so because they believe it answers questions about the meaning of life, and so they're exploiting the concept of the one. And you seem to address that a little bit in your book by saying, and this is a quote, "Such mindsets are based on imposing a predetermined image of, quote, the one onto the world instead of undertaking the attempt to honestly reconstruct the one out of its appearance as a dazzling array of multiple things." So what exactly do you mean by that? And, how do we educate people about there's a difference between what you're saying and the concept of the one with respect to quantum mechanics and some of these New Age pseudoscientific notions?
Yes. So I think the most important thing to say is that we don't have direct access to the one. We can't really observe it. We can't really make experiments with it. Again, since decoherence prevents us from accessing this quantum reality. What we can observe in experiments is always the classical reality. And so when we say what I think makes sense is very obvious that there is a fundamental quantum reality underlying our classical experience, then we need to use our classical experience to reconstruct this fundamental quantum reality. We cannot just make things up and say, there's this fundamental reality and I want it to be good, or to listen to my prayers, or to support homeopathy or astrology or whatever. We cannot just impose what we maybe want the universe to be onto the universe, but the universe is what it is, even if we don't have direct access to it, and we have to try to reconstruct it out of what we can see with scientific theories and with experiments and so on.
So is this kind of like backwards induction or inductive reasoning or deductive reasoning, or you're saying, we look at the many things that are out there, and the concept is that those many things are also the one and are all things. And so are you saying that we can reconstruct or construct a deeper understanding of the universe as one by looking at this decoherent reality that we live in?
Yeah, I think it's not so different from what we always do in science, right? When we do science, we have a limited number of experiments and data, and then we develop some theory which explains these data. And we don't have direct access to the theory. We just have access to data. We have just access to experiments, and we see whether these agree with the theory or not. And in a similar way, when we say that our classical experience follows from a fundamental quantum reality, we can look at our classical experience, we can look at experiments, we can look at data, and try to develop a theory for this fundamental quantum reality. And then we test it with more and more experiments. So it's not so different from what we always do in science.
So it would be similar to having water or a water molecule and then being able to deconstruct that water molecule into its components of hydrogen and oxygen, and then even go further into the nucleus and then into the nucleons like we've already done and get some concept. That's how we've understood the quantum world in the first place, is by, seeing, this reality that we live in every day, and then asking, well, what is it made of? And so we peel back the onions and we've gotten down to the quantum level. And you're now proposing that the universe itself is quantum in nature. Is that right?
That's right, yeah.
Yeah. That's fascinating. So, one of the reasons I wanted to have you on the podcast is that there seem to be, from the very beginning, serious disagreements on how to interpret quantum mechanics that still exists to this day. So maybe you can give us an understanding of the nature of those disagreements and how you feel the concept of the one that you're putting forward may lead to resolving those disagreements. And also, who were some of the main characters in these disagreements?
Yes. I briefly mentioned it before. So there is this problem that quantum, the central element of quantum mechanics, the quantum mechanical wave function, which makes the predictions, what we see in our experiments, is not directly observable. And early on, people who were instrumental in developing quantum mechanics disagreed what that means. So Werner Heisenberg was the first one who came up with the theory of quantum mechanics, the so-called matrix theory. And this was a very abstract theory. And so he had no really an intuition associated with it. For him, this was just an abstract model to solve problems and make predictions. So it was a tool. And he later on collaborated closely with Niels Bohr. And Bohr also thought from a more philosophical background that everything we really can talk about or make meaningful statements about is classical reality. So everything quantum is just a tool. Erwin Schrödinger, who came up with this wave equation and this wave function, which was more intuitive, also had a more intuitive relationship and thought that this wave equation tells us something about nature. And Schrödinger at the beginning was a little bit wrong about what this wave function really is. He thought that's really a wave such as a water wave which propagates in the usual space, but it doesn't. It propagates in some abstract space of possibilities. But so these were the two camps. Then later Einstein came in and he was very skeptical of a theory which doesn't have a concept of reality as a basis. So he also was opposing Bohr and Heisenberg, again from a more philosophical position. So this was the beginning of the argument. There were Bohr and Heisenberg on one side and Einstein and Schrödinger on the other. And then Heisenberg and Bohr were more collaborative than Schrödinger and Einstein. So they had more collaborators. They also contributed more to the development of the new theory. So they were more influential. And then for some time, this idea that quantum mechanics was only a tool became the orthodox interpretation. But at the same time, many physicists didn't really care. They thought, well, if we can use the theory to make predictions for our experiments, and if we can use it to describe things in particle physics and nuclear physics and solid state physics, then it's fine. This metaphysical pondering about what the real nature of reality, that's not really important and it's not part of physics. And so over the years, more and more people came in and questioned this orthodox idea of Bohr. And David Bohm, for example, was important. He came up with these hidden variables. He wanted to restrict the quantum realm to what we actually observe. And then Everett, he embraced the quantum reality and he wanted to expand the notion of reality to include all these possibilities of quantum mechanics. And I'm with Everett, as I said before. I think the quantum reality is fundamental, and everything in the quantum reality is part of reality, and we should embrace that. And I also think that for a long time, it wasn't really important whether we think it's a tool or whether we think it's reality. But now we come to problems we can't really solve anymore. And maybe now it is a good time to take a step back and reconsider what is the basis of physics, actually, the foundation of physics. And to think again what we consider as the physics reality. And from that basis, start to develop our new theories about space and time and matter.
Mm-hmm. And so how does the concept of the one help us do that?
Well, since so the one has implications. I mean, first, it means if all is part of a single one and constituents are really not fundamental, then the typical approach we follow in particle physics on string theory, that we look at higher energies and smaller distances and smaller constituents to find the most fundamental description, at some point will lead us astray. At some point it doesn't work anymore, since at some point we see that the most fundamental thing is not a particle or string, but it's the universe itself. And so there might be new phenomena that the physics at very high energies and very low energies, that there are some relationships between these realms which are non-trivial and which can have effects on experiments. So another thing is that if there's only one thing, the question is, does it make sense to think of space as fundamental? Usually space is just the relative order of things. We think of space describes that one thing is here and the other thing is left or right to it. And if there's only one thing, space is somehow meaningless. And a similar argument can be made for time. So we can think most probably of this ultimate reality as being space and timeless. And then this view that everything follows from a fundamental quantum reality, from a fundamental description of the quantum description of the universe, can help us to understand space and time as emergent properties of our perspective. So it redefines a new foundation of physics from where we can start to ask these important questions about the nature of space, time, and matter.
I understand. So, but the question that would ensue from what you seem to be describing is that how do we get access to the one so that we can understand that nature that you're talking about, or how things emerge from the one? Right now, we don't seem to have access to that, as you were saying earlier.
Right. We need to develop theories about the one, and then go on from these theories and try to derive in a deductive way predictions for experiments or properties of the universe, which we can find in our observations, in our experiments.
So are you working on such theories?
I'm actually very interested in this possible interplay of physics at very high energies and very low energies. So the technical term for that is UV-IR mixing. So physicists call the physics at high energy the ultraviolet, since waves at high frequency and high energy correspond to ultraviolet light, and infrared is low energy. And so there is a group of non-vanishing group of people who are interested looking into that, whether these two realms, which usually are considered to be separate in the traditional approach to quantum field theory, whether they could have some interplay. And I think this is very interesting. So there was a workshop at CERN at the European Center for Particle Physics earlier this year, and I attended that, and I think this is very interesting. And then also my professional expertise is actually in neutrinos. Neutrinos are specific particles, and I think neutrinos could also be very good probes for this kind of physics.
Mm-hmm. Could you say a little bit about neutrinos and why that might be the case? Neutrinos seem to be fascinating, nearly massless particles. We were talking about that earlier, and I was trying to recall some recent research that was done at CERN and now I remember what I was reading. It was really about establishing that neutrinos really do have mass, and there were some specific experiments that were done that established once and for all that a neutrino really does have mass, that they are not massless. But anyway, could you explain what a neutrino is and say a few words about that?
Okay, yeah, I think I know what you mean now. Right. So, neutrinos are particles, fundamental particles, such as the electron, which makes up electric current, which comes out of your socket if you turn on the light or whatever, or as quarks, which make up the protons and neutrons in the atomic nucleus. But neutrinos are different since they are very light, much lighter, 1 million times lighter than the electron, for example, and they interact very little. So in every second, billions of neutrinos go through us, through the Earth, through everything, and we don't really feel it. So neutrinos are, very, very, they hide from us, but they are everywhere. And so what makes them interesting is that we have data about neutrinos. Neutrinos of very high energies, which were produced in different galaxies. So there are these big neutrino telescopes at the one in Antarctica, giant detector in the Antarctic ice, which actually uses the ice as the detector. The neutrinos produce some light flashes in the ice, and this is detected. And they have found neutrinos which very likely come from distant galaxies and which have very high energies. So that means they traveled across a large portion of the universe. And with high energies, they are very sensitive to the to gravity, since gravity couples to energy as well as it couples to mass. So neutrinos could be a very, very sensitive probes to everything which is new about gravity and every unusual properties of the universe. There are other things like neutrinos have no charge. So that means they can be their own antiparticles. So they can be related to the question why we have more matter than antimatter in the universe. And one thing which is also expected from quantum gravity is that it doesn't respect charges which are not related to forces. So if the neutrino would be different from its antiparticle, that would be a charge distinguishing neutrino and antineutrino, which would not be related to a force, not like the electric charge, where a positive positron, the antiparticle of the electron, has a different electric force than the electron. So these are ideas which make the neutrino very interesting as an experimental probe. And the ideas to pin down that neutrinos actually have masses, they are related to neutrino oscillations. So we have two different types of neutrinos, and neutrinos can shape their can change from one type of neutrino to the other type. They oscillate between these types of neutrinos, and this actually has been seen already in the experiments the 2015 Nobel Prize was giving for. And now there are new experiments underway. Something is actually built at CERN, and there will be a bigger experiment at Fermilab in the United States, which will send a neutrino beam all the way to the Sudbury mine, and they will probe these properties and these neutrino masses more accurately.
Yeah, I understand. Fascinating and mind-boggling at the same time. Back to this notion of the one and trying to get an understanding of it. You use a lot of analogies in your book, and of course, the one I'm the most familiar with is Plato's allegory of the cave. And could you explain that allegory as it relates to this concept of reality and what we see as being an illusion, and what is producing that illusion as being real? So in other words, in the allegory of the cave, these people were chained and there was a fire behind them, and shadows were cast on the wall of the cave, and the shadows appeared to these people that were chained there to be all that there was. That was reality for them until someone escaped and went up out of the cave and saw that there was something else, which is your concept of the one. You can go there and there's something behind really producing that shadow, which is actually an illusion. Could you talk about that just a little bit, and maybe how that might give us a key to how we might actually access this concept of the quantum universe as one?
Yes, very similar to the shadows the prisoners see on the cave. The shadows are just a projection of the reality. And so very similar to the prisoners, we can only see projections of the quantum object somehow. So we see the quantum object as a wave, we see the quantum object as a particle, we see it as a specific position or something like that. But we don't see the full fundamental quantum reality. And in this sense, there's a similarity. We believe what we see is the reality, but it makes sense to argue that there's a more fundamental, more complete reality beyond that, which is the quantum reality.
Right. And this is an ancient idea that you brought forward. And of course, it was part of, Plato's quest to understand reality and what it meant. And of course, I encourage our listeners to go back and read Plato and the allegory of the cave. There's a lot more to it than what we're discussing right now, because he goes on to talk about reality in a far deeper sense and the purpose of man or humanity on the earth and what that all means. And reading Plato is fascinating. And I think to some extent it gets back all the way back to my original question about you asking deeper questions about reality and the nature of life. So we need to wrap this up with my final question that I always ask. And was there one event in your life that was transcendent or that changed you in some way and made you a different person or changed your entire outlook on life?
Well, I think there were many such events. I mean, it's not just a single event. I mean, being out in nature was always important for me, being on sailboats or surfboards or just running in the rain, meeting my wife, the death of my father, the birth of my son. I mean, these were all very important events. With respect to this idea of the one, I think what was important for me also was to live on Hawaii. I was a postdoc in Hawaii for 2 years. And living on a small island in the middle of a vast ocean, where you are quite often outside and in nature, gives you a specific feeling that you are not separated from the rest of the world, that you are dependent on nature, dependent on your surroundings, and that you are related to it. And I think this gave me a more intuitive relationship to this abstract formalism of quantum mechanics in some sense.
Great. Well, that's a great place to leave it, Heinrich. Thank you for chatting with me. Life is a story we tell ourselves. I think our listeners are going to enjoy this, and they can certainly go to our website and learn more about you and your book, The One, which is absolutely fascinating read. And I hope to have you back again to talk maybe a little bit more about neutrinos, and as you develop this theory on The One. I'd really like to hear more about it. Thank you so much, Heinrich.
Yeah, thank you very much.
Thank you for joining us on this episode of Life is a Story We Tell Ourselves. The book we were discussing is The One, and it's available on Amazon. Please subscribe to the podcast, and again, thank you for joining us. Remember, stay safe, share happiness, and never stop questioning. Curiosity has its own reason for existing.